again. We're almost through our course. We have 2 weeks to go. This Thursday we're going to have a guest lecture. So most of the time during Thursday will be spent on someone from Asset Inside, the company of Volker Will and Volker Wissels, to tell something about asset maintenance and how to use machine learning and predicting things and so on. For this morning, we're going to continue with the neural networks. Last week I did an introduction on neural networks, how they work, how they are built, and so on. Yes, question?
About the guest lecture, I saw that there was twice again Thursday.
Yeah, we have one on Thursday and next week as well.
Yeah, but
probably.
So that we know that most people probably chosen online then.
Okay.
Because it's like
This Thursday.
yeah.
Okay. All right.
Wednesday and Thursday as well.
Okay. So, well, in that case, yeah, we're going to do it online.
Yeah.
In this case. Okay. Good to know. I'll check it out. Check it out.
That's on the side of Insecto.
Yeah. Okay. So maybe we're going to move into next week. Well, I will check it. I'll check it. Okay. So last week we talked about neural networks and how to build them, how to use TensorFlow for it. And I did an introduction on CNN, the convolutional neural networks, which is a specific type, very suited for recognizing pictures and trying to predict and classify pictures. This week I'm going to do a quick recap on what CNN was again, because that's important, because CNN will come back in all kinds of new developments when it comes to new algorithms for machine learning. I will talk about recurrent neural networks. It's also a specific neural network. I will talk about long short-term memory, which is also a recurrent network, but it's an improved version with more memory, which is important. I will tell you about it. Then I'm going to go over to generative AI or machine learning, which is a hot topic these days. We've seen a lot of developments, and I will expect a tsunami of all kinds of applications in that area in the coming, let's say, weeks, years to come. And I will talk about the most important ingredients for generative AI, and that is the autoencoders, very important. I will talk about the next invention around 2016. That's generative adversarial networks, a specific type of neural network for learning how to produce, let's say, quality and high quality type of pictures. And the latest one, stable diffusion, which is again a new technology that is now being used also in GPT-4, which is the latest OpenAI algorithm that they use for, generating pictures from text or generating text from text and so on. So that's the newest kid on the block, in fact. So I'm going to tell you how in essence it works, given the other ingredients that are listed here in this overview. So again, we are here at the bottom of all these new machine learning techniques. Just a quick recap on what CNN was again. I told you about the common neural networks, which are fully connected with an input layer. The number of neurons in the input layer is equal to the number of features in your input data, or equal to the number of pixels or pictures that you want to input. And the output will give you, let's say, 1 neuron for each class, or 1 neuron for your regression output, which is a number, basically. This is a specific type of neural network where we have different type of layers. We have convolutional layers, we have pooling layers, and we have flattened layers. And the most important ones are convolutional layers. They are specific type of layers which take out specific features from pictures. So if I have a picture over here, what I'm going to do is I'm going to multiply it with this filter. This is, in essence, this is a filter, right? And I'm going to go over with that filter over the picture, and it will generate a number. And that number is going to be a part of this feature map in the next layer, right? And I'm going to use multiple filters. So I'm going to have multiple feature maps, which are in essence filters. So for example, I could have 10 of these types of feature maps. And the weights of these filters here, they are being trained. So the training algorithm will also decide, okay, what will be the best type of filters in order to get the best match, you know, to distinguish the features from the pictures. During training I can decide, okay, which step size do I take? How quick do I move this filter over the input picture? Is that step by step, or I could skip pixels, for example, to make it faster. And I could add, because if you do this process, the output will get smaller. If you want to keep the same, let's say, dimension of your picture, you can add zeros, let's say, around the picture, so that your output will have the same size as your input, right? So that's a convolution layer. We also, in a CNN, we have pooling layers. In fact, this is just let's say, subsampling or downsampling, because we have an input here of 4 by 4 pixels. We have the pixel values here, right? And I'm downsampling it here to 2 by 2. So in this case, I have a reduction to 25% of the original, right? So it's downsampling, let's say, factor 4, okay? So that's also a part of a CNN, and this is also a dropout layer. It's also part of a CNN, which means that in a certain layer, in the dropout layer, I'm just randomly going to take out neurons. What was this for? Do you remember? Why do we have dropout layers in a CNN? What's the reason? Sorry?
Did you already tell us?
Yeah.
Yeah. I thought it was for preventing overfitting.
Correct, Paul. Yep, that's to prevent overfitting and to generalize better. And yeah, in practice, it means if you take out some neurons in a complex network, it will generalize better. It will still have the similar output, but not overfitted. So that's why we do it. Okay, so this is then how such a network looks like, a CNN, for recognizing pictures. For example, classifying cats and dog pictures and telling, okay, this is a cat and this is a dog. And it does this by using these convolution layers, pooling layers, and then dropout layers. And in the end, you still have a regular neural, fully connected network in doing, for example, your classification, in this case, recognizing what's on the picture. Okay? So that's how CNN works. I'm telling you this because this is an important part also when we talk about, like, for example, the generative adversarial networks or the stable diffusion technology. Okay? Question? Somebody online?
Power off.
Oh, power off. Oh, okay. Okay. You still have the mic running?
Yeah, the mic is the other. That one
Okay.
didn't work.
And oh yeah, to finish off CNN, this is how you can build a CNN. We have a learning curve over here. This was the example where we use a CNN to recognize the handwritten digits, right? I put the example online, so it's on Canvas. You can run it for yourself, and you see that during the training here you have the number of epochs, right? So the number of times your data, your input is going through the network. You see that the loss is decreasing and accuracy is increasing. So that's what we want to see. And if you compare it with a regular neural network, we had an accuracy of 87%. And with the CNN, we can reach already, quite simply, go up to 90% and even more. And we can improve it by tweaking this network further. Okay? So in 90% of the cases, it will predict the right handwritten digit in this case. Okay? So the next type of neural networks is what we call a recurrent neural network. And what's special about recurrency? Well, it is in fact that normally we would have a forward, let's say the information flows forward through the neural network. In this case, you will have some feedback in between neurons. So the output of a neuron will also work as input for the neuron, right? So we have feedback loops. And we use it to analyze time series data everywhere where we see, let's say, regular patterns coming back, like in audio or in time-based information or stock data, etc., which is time-based. We can use these kind of recurrent neural networks to predict better because there's some sort of a memory built up within that network, which is larger than what we can achieve with a CNN or a regular neural network. Can be used for natural language processing because we can predict longer sequences of words. Yeah, so we have sentences that we train the network on, and we can then predict the next words in the sentence. Basically, also how ChatGPT works, trying to predict what's coming next. Okay, so this is how it looks like. So we have a neuron, and we have an input here. In this case, usually we're drawing the neural networks from the left to the right. We have the input on the left, and the output on the right. For the recurrent neural networks, we always draw it in this way. You see it in the literature. Input is coming from the bottom, going through the neuron, and the output is generated on the top. But in this case, we also have the output going back into the neuron again. Right? So in this case, this could be a vector, so multiple values, let's say multiple features, and the output here is a scalar, so it's just one output number in this case, for example. So this is the most simple recurrent neural network, only one neuron. Remember in the beginning we had a very simple neural network with only one neuron, and we could easily simulate linear regression with that one, right? Because the weight was the, let's say, the coefficient, and the bias was the, let's say, the constant that we see in a typical linear regression with one input value. Okay? So in this case we also have this simple network, and because it's time-based, because it's recurrent, we can, let's say, this feedback, we can also draw it like this, that the feedback is coming to the same neuron, but then one time step later. So if we write this out, in fact, we will have this situation over here, right? So we have the input here, and then the input is going to the same neuron, but then a time step later. So we call that unfolding the recurrent neural network. So in fact, this one will look like this one if you put it in time. Yeah? If you display it in time, like this. Okay, so how do we train this? Well, also with backpropagation, but then we call that backpropagation through time. So it's a similar technique, but now we're going back like this, right?
Yeah.
In time. Yes?
But for my visualization, is the data not kind of piling up because you have a data stream from the X and there's a data stream from the Y again feeding in? So
No, it's not piling up. For example, in this case, we have, let's say we have 3 features as input. So in this case, every feature is, first feature is here, input here, the second one here, the third one here. And that will be fed in here. Yeah? And again, this will, let's say the last feature, or the oldest feature, more or less will disappear in time. It's the effect of it. Because the last feature fed in this case, will have the most influence on the same neuron. So in time, your input is going to disappear. That's the problem also with recurrent neural networks, that in fact it's not adding up, it's decreasing in time. So if you want to improve that, and let's say if you want to predict words in a sentence, then we want to have this still in memory in some way. So there's a drawback that we can solve. We'll come back to that later on. Yeah?
How many neurons can it go through before it forgets the one?
Depends on the situation. But in general, let's say after 10 timestamps in a normal situation, let's say your input might be disappearing already. Depends also on your input. So it can be different in different cases. But that's the problem, that your, let's say, the oldest information, in this case, will disappear in time. The effect of it will be less. It's kind of hard to envision, obviously, because this is in time, rolling out in time, but I will give you some examples so you can have an idea how this will in effect work.
So
Right?
it looks a little bit like the moving average, where you all the time take 90% of the new input and 10% of the old, and
That's it. That's it. It's similar like that. Yeah. That's the reason why the oldest input has less, in the end,
Yep.
less effect. And that's a problem sometimes because we want to keep that in memory. Okay. So what you can do, you can replace that one neuron also by, for example, 5 neurons like this. Yeah? So your input is not only then a vector, but your output is also can contain multiple values in this way for each neuron, right? So then in fact it works like this. You have some sort of a memory. It says here typical 10 steps, as I already said. After 10 steps, you can think that the information which is fed in here will not have much influence here after 10 time steps anymore. Okay, so there are different kinds of recurrent neural networks. We have 4 types. The first one we call sequence to sequence. So we input a sequence of, for example, words or letters, and we have an output also of a sequence of words or letters, maybe one timestamp ahead in time. Right? Examples: stock prices over the last 5 days. Your output will then shift by 1 day, so you have the last 5 days here, and the output is the last 4 days, plus the latest one will be in effect your prediction for tomorrow. Okay? So it's shifted then in time. We also could have a sequence to vector network, where your input are multiple features or timestamp data, and you have only one output in the end. It could be something like a sentiment score. So you input a lot of words, and in the end you want to know, okay, is this positive or negative, or how positive is it, or how negative is it, for example. You could have a vector to sequence the other way around. So you input, for example, let's say a caption for an input image, and then here your pixels, your output, your pixels are coming out for the picture that you're describing. It's also a possibility. So that comes close to what we see with ChatGPT and so on, and also Stable Diffusion, where one sentence or a few words will generate, in effect, a picture. Right?
But the step to the right is still the time step, right?
Time step.
Yeah. Oh wow.
Yeah. And encoder decoder, I'm coming back to that because this is very important. We have then an input here, it's an encoder, but then this information will first flow to this section and we'll have an output over here. So it's also shifted in time. So it's sequence to vector and then vector to sequence again. Right? So they are kind of hard to work with, I must say. So in practice, RNNs are mostly still used for like audio type of information. But now I showed you an example where in fact you could turn audio into picture data. So since we have more improvements in the picture area, which is interesting to translate audio problems, for example, into a picture domain. And how do we do that? For example, with the short-term create transformation that I explained to you later on, where you take a, let's say, small sample of a piece of audio, and for that small sample you translate it into a frequency domain, so we can see, okay, what are the different frequencies and how, let's say, how much are they in your signal, and then you put these frequency domain pictures, let's say, next to each other, then you get a picture, right? And that picture can be your input for your CNN network. And that can be used to classify, for example, to make a difference between yes or no. Or a piece of audio with yes inside, or a piece of audio with no inside. Translate it to a picture domain and use a CNN instead of a recurrent neural network. That's what we see nowadays. But still, I want to tell you about this one because it's still used in some cases. What you even can do, we saw in the former pictures, we saw just one neuron for each timestamp, but you can also make deeper layers. Again, your input in this case is on the bottom and your output is on the top. So here in between we can have different hidden layers as well to make it even more complex, right? Because this is quite a complex situation, right? So let's see how this works, also in TensorFlow, just to give you an idea. I have an example, which is also, you can find it on Canvas, where we generate time series, 10,000 time series items, And each item of these 10,000, they will contain a signal. So it's one value per timestamp and then 80 timestamps. So each time series has 80 steps, and the value that it will have, it will be between -1 and +1. So it's a signal, right? So it's in fact per timestamp one value, right? To make it easy. Could be something about, let's say, put a sinus wave for 50%, add a 20% sinus wave with another frequency, and add some noise as well. So we generate some artificial time series data. And we produce 10,000 of the examples, each containing 80 steps. Could look something like this. In this case we have 50 steps, but we generate it's all looking like this. Yeah? So 2 frequencies with some noise. This is. Okay? Ranging between -1 and +1. So when we do that, what we want to do is use these 50 steps of the series to predict the next 30 steps. So what we do, we split the data into the first 50 steps is your input, and the next 30 steps is your labeled data, your output that you want to predict. So you do supervised learning, so you put in these 50, every example with 50 timestamps in, you're going to look for the next 30 timestamps. Okay? Okay, so first possibility is a sequence to vector type of solution, where, as you can see here, you're putting in 50 timestamps from t0, so at every timestamp, in fact, you're putting in your first value. Next timestamp, the next value, and so on. So this one, all these values here, they are put in like this, until here. So we have 50 timestamps as input. And what will we generate? Well, at the last timestamp, we want to generate 30 outputs, so a vector of 30 values. It will look something like this. So with this input, we're trying to predict this output. So we're going to train this network doing this. And this could be used, for example, to predict stock developments as well, right? So this is a possibility. Input 50 timestamps and output at once as a vector 30 timestamps to predict, okay? How does it work in TensorFlow? Well, again, you have to import it, and here I'm generating my time series. As you can see here, I take two sinus waves, add them up here with some random noise, and then I have 10,000 of these batches of examples, artificial. Then here I'm going to split it. First 50 will be my input, or the x values. The next 30 for each sample will be my output, my y values, right? That you can see over here. Okay, so how to run then an RNN? Well, here you have to first create the RNN. Here you can see I have 60 input neurons in this case. So again, these 60 are over here. Here, see? Each time I have 60 in the hidden and 30 as output. Okay? So, coming back here you see 60 over here. Yeah? And here you can see the 60 neurons and the 30 output extra steps I define as 30 over here. So, I need to build it. First specify the model, build it, and then train it. And here's my fit with the X information, Y information. I'm running 20 epochs in this case. Okay? And then it will look like this, for example. So prediction of the next 30 steps. This is my learning curve. Here you see the number of epochs. I've run this, you could do it for yourself. I have the code in Canvas, and there you will see in your learning curve that the training loss is decreasing, that's what we want to see, and my validation is going down as well. Yes, Finn?
What's an epoch?
An epoch?
Yeah.
That's, let's say, feeding in all training data once into a neural network. So I'm continuously feeding in and training my neural network by feeding in the input data, if I have input all, in this case 10,000 examples, then I have run one epoch. So I keep continuing because one epoch is not enough. My loss is too high. So I'm going to do another epoch. I again put in all input data.
20,000.
So 20,000. So in this case, 20 here is 20 times 10,000 examples being fed into the neural network. So as we do that, you will see that the loss is decreasing. Yeah, optimally we would have like to have it down to 0, but this is 0.02 is not that bad, in fact. Okay? But as you can see here, it's kind of stabilizing here, right? And if we keep continuing, I told you about it, what will we see?
The validation will rise.
Validation will go up, and the training will continue to go down, right? And we call this overfitting, right? Okay. So, what is the effect? Here I have my 50 input steps. This is just one example. After we do a prediction with the model, after training, we predict it with one example. And if we do this, I'm printing here the 50 inputs. And here I've printed both the actual values in red and in blue the thing that I'm predicting. It's pretty close, right? So that's what we can do with recurrent neural networks. But obviously, yeah, that's how it goes in machine learning. Every method has its drawbacks, so how can we improve? And still, the drawback here is that long sequence training requires a lot of training before training loss goes down. And these are all the kinds of problems that we see with regular neural networks. So it might take too long, and it will forget its first inputs after 10 timestamps. It maybe have forgotten about all the values before. Okay. So how to solve this? Well, this is another type of neural network. It's called a long short. What was it again? Long short
memory.
Yeah, term memory, right? Yeah. And how does it look like? Well, it looks like this. If we open up the neural, this is a specific type of neural. In fact, normally you would have one output or one feedback to the next neuron, and one output over here, and one input here. But now we have two feedback loops. And one feedback loop is the long-term memory here. And we have a long-term state called, and we have a short-term state. So there's some form of memory here created in this neuron. In order, through all these timestamps, we try to memorize what's going on. And we have here, let's say this is coming from the timestamp before, your long-term state. And this is controlled by your input, your short-term input. Okay, are we going to forget some information or not? We want to input, let's say, the new information and add some of it also to the long-term state. And we want to control, let's say, the short-term state as well. So it's kind of, and all of this is being trained, obviously, as well, to have the maximum output, right?
Is that H kind of like a kernel, or?
No.
Okay.
No, it's just, as you can see here.
Oh, it's from the previous
here we
cell.
have
Oh yeah,
the
sorry.
layers inside
Yeah.
that are actually driving these gates.
Yeah, but it's the output from the previous cell. Yeah, sorry, I misread.
This
Yeah.
is the output, the
Yeah.
feedback
Yeah,
to the
of
next
course. Yeah,
timestamp
still
neuron.
Yeah.
Right? So this is basically how it works. We have these, let's say, activation. Here we have, let's say, the information itself, and this is, here we see the logistic function, this one, to control either 0 or closer to 1 to control these gates, right? This is the control gate, and this is control gate, and this is also a control gate. And it's being driven here by a logistic function between 0 and 1. It's kind of complex, but the idea is, okay, we're going to create two feedback loops. a long-term state with more memory and a short-term state in order to keep more memory. Yes?
Explain again, I follow just one of X and then how it goes to the end.
Well, here is your long-term memory coming from a timestamp before, right? And here we're going to decide, okay, what information, which is depending on the short term from the former, let's say, series, how much controlled with this one, these layers, how much are we going to forget or not? What are we going to delete? And then here, how much are we going to add to it from the short-term state, from the, let's say, the past timestamp? And that is then put in as the new long-term state. So something has been deleted and something has been added, basically. And for the short term, some of it has been taken from the long term and some of it has been taken from the short term as well. Right? So this is basically how it works. And the idea is to keep some memory and put that in the information here. Right? To overcome this memory problem. So how will it look like if we do the same thing again with a long short-term memory? It will look like this. For example, I will put in my 49 time stamps over here, and I will output these 30 ones predicted over here. And what I can do is I could have a sequence to vector. This is a vector only at the end, predicting 30 timestamps at once. I could also do a sequence to sequence, which means that at every timestamp I'm predicting the next one, or the next 30 rather. So at timestamp 0 I'm predicting 1 to 30. And in the end, 49, I'm predicting 50 to 79, which is in the end the 30 that I wanted. And this is better because it will retain more memory. And if I do that, this is how you do it in TensorFlow, predict 30 values at once, or predict 30 values at each step, the difference that I just showed you. And you can see here the difference in color. I'll come back to you, I think. Then you're going to see that this one, here are some results. This is sequence to vector, and this is sequence to the sequence, and this one has a loss, you see here, which is around, well, lower than 0.01, whereas the sequence to vector is 0.02. So if we output at every timestamp also the 30 outputs, the next 30 outputs, it shows that this one is more accurate. Okay? Think.
The predictions from like 1 after instead of the 30 after?
Yeah.
Every time? Is that like the short-term memory that's
No.
extra?
No, no,
Or the long-term?
both, because in fact, here, these ones, they will contain both short-term and long-term. So it will, for every time step, that information is fed to the next time step. So the short and long-term memory will be here in between these timestamps every time. So it will build up. So in the end here, maybe after timestamp 49, you would still have, let's say, long-term memory here inside these long short-term memory neurons coming from maybe timestamps 50 times ago.
Yeah, but how is this picture different from the other one?
The difference is that in fact you see here one arrow, but in fact there are two arrows. That's the difference. So normally we would have only one feedback, which would contain, let's say, information, but with the long short-term memory it's split up between, in fact, two, for short-term and long-term, which means that in the end here, I could still have information which is valid over here. And that means that, let's say, if I have some information here in the beginning, that might be relevant for what I'm putting out in the end.
So this
Or-
one should have 2 arrows.
Yeah, in fact, yes.
Because that would, like,
I will
this
change it
looks
next
exactly
time.
the same as the other
Yeah, I
one,
will change
so-
it next time. I will change it. That's correct. I will put in 2 arrows there just to make it easy. Yep.
And
Okay.
for the last one, the last timestamp, we can also have the short-term output, yes?
This one's?
No, the last one. Yeah.
This one?
Yeah.
No, because you stop here, in this case.
Yeah, but,
No feedback. You mean no feedback loops over here?
If you not stop and get a short-term output also from this one, can we compare all the short-terms to see how they can correlate with each other? How they can affect each time stuff has some effects based on short-term output to the other one, yeah?
Yeah,
So the last one would be really different from the first one.
sure. And it's all affected by all these timestamps over here. That's for sure.
And we cannot, take something out of that.
Well, the network is trained to see what is important and what not. So that's the beauty. Also with CNN, the network itself, due to training, will see which features are important and which ones are not. Because you have to, it will be trained in those features that really make a difference. Like in PCA, you really want to put out, let's say, only a few dimensions, and that's being trained in the network itself. And it's the same here. Yeah? Okay. Again, this is how it is done, and when we talked about LSTM, this is the result as I showed you. Okay, so far about recurrent neural networks. Next topic is the generative AI, ML, which is a booming topic. There was a congress a couple of weeks ago in Austin, Texas, South by Southwest. One of the, let's say, where even our minister was over there, and has been a lot of talk there about the GPT-4 that has been released, and I will expect a tsunami of all kinds of applications. For example, I heard something yesterday about a company that is using all the data from the elections of political parties to try to be able to predict, okay, what's the best choice for you. So by inputting that data and all the different programs from the different political parties, you'll be able to learn, yeah, what to do and so on. So you can ask questions to the model, what do you think about windmills on land, for example, and if you are against it, for example, which party you have to vote for. Yeah, things like that. There's a lot to come, and also in the area of content generation. So what is then generative AI? That's a new breed, in fact. So we're talking about algorithms that are capable of generating data, and not just random data, but data that is similar in some way to the input data. Variations of the data that can be variations on text or on images. And the beauty is that these generative algorithms, they are trained on large amounts of data, but you don't need a lot of data input on that model to have it output good quality of content. So that's the beauty. Normally, with neural networks, you have to put in a lot of training data to have it, let's say, do the things that you want to do. In this case, the algorithms are already pre-trained. So just, let's say, a few words are enough to let it generate things. Okay? So it's already pre-trained. So it's unsupervised learning, basically. And so you can run it with relatively low quantities of data. And it's also available through APIs like ChatGPT, so you can do what's called prompt engineering. So by asking the right questions and prompts, it will output the good data I will show you.
But how is it trained? Because it should have some sort of label.
I'll tell you all about it. First, I want you to understand what are the basic building blocks in neural network terms, and then we come back to your question, okay? So, what can you do with generative AI? Well, you can generate content and ideas. So during the design process, I think we're going to see a lot of developments. We know it's already built into Photoshop and all kinds of other Kafka type of applications where you can easily dream up new content and so on, or automatically produce videos, etc. This is also important, improving efficiency. A lot of companies are looking into, okay, how can I get rid of dull work? For example, reading through, let's say, what do you call them, invoices, for example, or typing in data and so on. How can we get rid of that? So getting rid of repetitive tasks in companies, and also creating content which is personalized, like the example about politics that I just mentioned, and chatbots and so on. We all know that. Okay? And you get things like that. I already showed you. If I have a picture here of here the whole solid bed, and I say, okay, generate a style like Van Gogh, you will get something like this, right? So and things like this. It's the website Deep Nostalgia. If you put in an old photo, it will generate video like this, right? Okay. So the first important building block for any generative network is what we call an autoencoder. And what is an autoencoder? It's a funny type of neural network, but it is used to encode data and to make dense representations of that data. That means, can we take out, let's say, the essential data from that input data? And this can be used for feature dimensionality reduction. In fact, PCA is something that you can do with an autoencoder. And you can use it for feature extraction, the things that we've also seen in CNNs, to extract features and to reduce, in fact, the size of the input. So also unsupervised learning method, and some of these encoders are also generative. And that means that you can use it to generate similar data. Okay. So, just for your idea, what is then, let's say, a dense information? What are we talking about? How can you reduce the size of any information? Well, look at this example. I have here two sequences, right? This is a short one, and you think, okay, maybe easy to remember, it's not so long. This sequence is much longer. So which one of these two are easiest to remember?
Second one.
To be, yeah.
Yeah.
There's a pattern inside. And that's exactly what we mean with the dense representation. So the only thing that I need to remember when I want to remember this sequence is, okay, I'm starting at 50. Every time I subtract it with 2, and I enter 14. That's everything I need to know. So that's what we call dense representation. So I want to take out these kinds of things from, let's say, huge data. What are the underlying patterns, right? Instead of trying to memorize this one. Okay. So, it's also, people that are playing chess probably know it, pattern recognition, yeah? That helps you to store information more efficiently rather than, let's say, having remember where all the pieces are on your board, right? So what is an autoencoder neural network? Well, it looks like this. It's kind of a funny neural network, but it has an input layer. We call it an encoder. That's why we call it an autoencoder. And we have an output layer. And what we're trying to do is trying to limit the size of a hidden layer in the middle. So what we're trying to do is, and what we are going to do, and that's funny, my input is, for example, this picture, right? And my output is the same. So what I'm trying to do is to have a network which generates the same output as its input. But in between, I'm forcing this neural network to reduce the number of features for my input to a, let's say, a limited size, by just limiting the number of neurons, for example. So I have only a few neurons there available, so I force this network to learn how to represent this picture in an easy way, in a limited way, right? So I'm training this over and over again until my input is exactly the same as my output, right? So, in the end, I can take away my output and I can do other things. So, the limited middle layer prevents the autoencoder to just copy. Otherwise, you could say, I just copy the information. No, I'm limiting this number of neurons here in the middle, so So I force it to learn efficient ways to represent it. Right? So that's a funny idea, right? That's what an autoencoder is. And this is the basis for all the things that we do now with generated pictures and so on, because we want to try to, find what we call latent representation of that picture. Just changing on one single thing here, we could generate a picture which looks like this one, but then different. For example, there might be one neuron here that represents the color of the hair. If we train an autoencoder to distinguish certain characteristics, by just changing something here, we could change getting the same picture, but then we change, for example, the color of the hair, because that's a feature that has been recognized here in this limited space. That's the basic idea.
So you kind of train it to know his own neurons, what it is.
You train it to remember to go down to the basic features of how to be able to recreate from limited number of features the same picture
But
again.
it should still know that that specific neuron is for the coloring.
Yeah, you have to tell it that. Then we are a step ahead, but that's one of the possibilities that you can do with this one. Right? I'll show you. But it starts here. It starts with the fact that my input is similar to, or the same as my output, and I'm training something that's called a latent representation that is smaller in size than my input or output. Okay? So I get an encoded dog image in this case. Try to remember this. So there should be some relation between input. Otherwise, it will be hard to train an autoencoder. Yeah? And in fact, this is what we call feature reduction. We are reducing the number of information. We try to compress it in some way, which is similar to what we've seen with PCA. There's also feature reduction. And in fact, PCA you can do with an autoencoder with just linear activation functions. So it's the same. So this is how it works, basically. If you use CNNs, then in CNN we've also seen this feature reduction. You're going through the big picture, through these convolutional layers and dropout layers to a small, let's say, representation of the picture.
Yeah, we were thinking, is this also how zip files work? Zip
No, that's encoding, looking in, let's say, how frequent certain items are representative in the data.
LLA run length encoding.
Right. So that depends
And
on
off mode probably.
So if you can encode your most frequent data in a very short way, and the things that are only, let's say, they are only once available in your input, that can be a long one because it will only occur once. But in this way you can compress the data and similar type of things. That's sorry? Yeah.
But actually also smaller, so
Yeah.
maybe that works the same.
Yeah, but it's more based on frequency analysis, basically. How frequent are items in your input. But it could be done like this again, because with an autoencoder you could also compress pictures. So it's the same. Yeah.
When you look at all the compression techniques, the JPEG, for instance, also uses all kinds of different stuff. So a lot of time it's not like it only uses this one, but it kind of piles on top of each other.
Dynamically.
Yeah,
Yeah.
it's really interesting stuff.
Yeah.
It's really nice. The video encryption is really impressive.
Yeah?
Because- yeah. It's enormous.
Basically also picture, let's say, picture compressing as well.
Yeah, but what it even does, it looks at the moving items.
Yeah.
So if it's just, that's why explosions is difficult. Because there's happening too much at once, and then it goes like
Yeah, football, for example.
Because it
If
wants
you
Moving every time.
yeah. If you switch from to a totally different
if something is completely randomized, then it's difficult to
yeah
replace it.
Right.
yeah, but you see it if you've got a JPEG with a lot of random noise, then the size of the final JPEG will be big.
Mm,
Yeah.
So it's
Okay.
So these autoencoders, they are in different shapes and forms. We could use them with deeper layers, obviously, like for doing PCA. We could use CNN layers, yeah, for compressing pictures, for example. And we could also even put in recurrent layers for an autoencoder. So you have all kinds of variations. So here in math terms, it is explained. We have an input, x, and we have weights here times the x, the x input information with a bias, and we put a sigmoid activation on it to get a latent representation, and the decoder will then take, and sometimes these weights are just mirrored if we're looking for the same input and output. Yeah. Here we're taking in the, let's say, this one, the decoded of the encoded information. We again multiply by the weights, we add a constant, and we put a sigmoid on top to get the output x here. And again, the most basic autoencoder, we try to do it in such a way that x is equal to the predicted x. So my so-called reconstructor error is the difference between those two, and my loss function, very simple, is the difference between, we can quadratize it to, make the larger errors stronger, yeah, like in root mean square error. We do the same thing. In this case, we're talking about this type of, so the absolute difference squared. It's my loss function in this case, okay? So we train the network in that way. And this is where it's all about. So we train it such that these features can be used here to reconstruct the original data. Okay. So we can use it for classification, for example. So once we have trained this, yeah, what we can do is to throw away my decoder. So we can only keep the encoder and all these weights, right? And then replace my decoder with a regular classifying type of neural network. Yeah? And then I have an output y here, and what I want to do is to train this again such that I'm predicting my input and label output like this.
But you're only going to change the right parts, right?
This one.
Yeah.
Right. And the advantage, you can say, okay, why do we need to do this?
Wow, cool.
Well, this is one of the things that we're seeing in Stable Diffusion, which is the latest algorithm for generating pictures, is to train this encoder. And we're going to use these latent representations. The advantage, because we can use large quantities of unlabeled data and only small quantities of labeled data in order to use this network. That's the advantage.
That's cool.
That's what we see with all these generative networks, right?
Wow. So, because we're doing vision with electrical engineering,
Right.
and the problem is always getting large number of pictures.
Oh, you are.
Yeah. So you
Okay,
take all the pictures from
So you can
yeah.
use pre-trained as well. There
Yeah.
are a lot of pre-trained
Oh, this is
encoders.
cool. Yeah.
Okay. So what can you do with it? What can you do with an autoencoder? Well, for example, you could use it to train it to have these handwritten digits denoised to regular digits again. Yeah. So removing the noise basically, or again, yeah, compressing pictures obviously because this is a dense representation. You could also learn it to really compress the data. That's the more easiest one. Or like how Google does image search, what you can do. Okay, encode your house information, and then houses probably will generate, if I train this on houses, it will generate the same, or a latent, let's say, representation which is very close to this one. So you compare it, and if it's close or the same, then you know that's also a house, right? So that's how you can use it. And the other way around, you could use it for anomaly detection or outlier detection, because you can train your encoder first on normal data, and if you input some other information which is quite different, then your latent representation will be quite different as well. So you can tell, okay, this is not a house, but this is not a cat or whatever, right? So I have an example also again on Canvas explaining how this works, how the denoising. Basically what we do in the example is we take the MNIST dataset with all these handwritten digits, we add some Gaussian noise, so random noise to it, and then we train the autoencoder to generate the original again, right? And then if we have trained it, we actually have a trained encoder or autoencoder that can do denoising of handwritten digits, basically. And this is how it works. I won't go into detail. You can run it for yourself and see how it works. We have layers for the encoder part, like this one. We have layers for the decoder part, or encoding. This is the middle layer. And this is the decoder part. We have some layers for it as well. Try to run it and try to train it and see how it will work with the denoising of your pictures and what accuracy you can have. So this is the autoencoder board. Very interesting. We will see it back again in the Stable Diffusion, because what we can see is that the, let's say, generation of data that looks, or pictures that look similar to other pictures is easier on latent representations than on the picture itself. It's much quicker. That's the whole idea of Stable Diffusion. Okay, coming back to that one. First this one, because there's a guy actually in Amsterdam, Max Welling, he's a professor there at Artificial Intelligence at the University of Amsterdam. He invented a variation of the autoencoder. It's called variational autoencoders. Basically the idea is, can we then variate some features in this middle layer such that we can generate pictures which look alike. You know? In fact, the beginning of pictures that looks like other pictures. So he started with that one. I think it was in 2014 or something. He's still active over there at Artificial Intelligence. And then another guy, it's called Ian Goodfellow. He worked at Google Brain, also at OpenAI, changed to Apple, and now he's back at Google DeepMind again. And he studied at Stanford University. He also got a Turing Award, so he's quite
smart.
Quite smart in the computer science. And in 2014, later on in 2016, he wrote a book. So if you're studying artificial intelligence, then this is your Bible, the deep learning, how to do deep learning. And part of this is how these GANs, or generative adversarial networks, work. That was a new idea by looking at neural networks in another way. How to, generate content that looks like other content. Okay? So, what can you do with it? Well, things like this. So you transfer it into another domain and change your horses into zebras and things like that. So it's mainly used for generating super resolution imaging, coloring, and so on. It's also unsupervised. And what was the basic idea of a generative adversarial network? In fact, that there are two parts in it. In fact, there are two neural networks that try to compete with one another. One is generating pictures, and the other one is trying to see, okay, is this picture real or not? Or does it look good or not? And they help each other to become better and better and better and better. So they compete, it's like a game. So they're trying to compete with one another. And we call that a generator. So the generator is generating pictures. It starts with random noise. So you take Gaussian noise, which is random noise, and from that one you're trying to generate picture. The first one will be worthless because it's just noise. And then the discriminator, the second part, will tell, okay, and it will be trained, okay, these are fake images generated by the generator, and I have real images. So I have a training set which contains fake images as well as good images. And I'm going to train my discriminator to see the difference between those two, because I'm trained, I have labels. I have labels from the generator, those are all fake, and I have labels on the training data, they're all real pictures. So in fact we're talking about a classification discriminator neural network that is trained on recognizing fake pictures, let's say outputting a 0, and real pictures outputting a 1, right? And by letting these two compete with one another, I'm trying to get the best pictures, or pictures that look like the other trade pictures as much as possible in such a way until your discriminator doesn't see the difference anymore and thinks, okay, this is a real picture, not a fake. Okay? That's basically how it works. This is it. So I'm starting with noise. I generate some picture. Then I have a data set for my discriminator. I have a data set with fake images and real. I know it. I have the labels. So I'm training with it. I'm training my discriminator to see the difference. The train is one, right? But then my generator wants to know how can I fool the discriminator to not see the difference anymore. So that is being fed back into the generator again to make it better. That's the whole idea.
So, and they get punished, the bottom one get punished if the top one
That's
is
it.
right,
Yeah.
and the top one is punished if he's wrong.
Yeah.
Cool.
Yeah. So again, generating random images. I have a data set for the discriminator, and that will decide, like a classifier, is it real or is it fake? Yeah. Binary classification. So it's like a two-player game again, right? The generator architecture looks like this, convolutional. So it's good at upscaling pictures again, and from noise generate pictures with convolutional layers. So here we see these convolutional layers coming back again. And how does it work? Well, again, these two neural networks, they have opposite goals. They're trying to improve each other. So what's happening? First, the discriminator is trained on this label batch between fake and real images. And that's usual training, is binary classification, right? Okay, then step 2, the generator again produces a new batch of new pictures and let the discriminator, with the frozen weights in the discriminator, tell if they are real or fake. Yeah? And then tune the generator, let it learn from backpropagation in such a way that the discriminator only sees once. Yeah? Okay, so that's the whole idea. So they start from scratch, they learn together, but it's kind of difficult. So there's a lot of research going on in this area, and I think by now, let's say the most has been taken out of the guns, and we see some drawbacks here because they're difficult to train, so that's why you see the whole AI community moving over to stable diffusion instead. So we are now full of a new idea, which is stable diffusion. I'm going to tell about it, what it is. If you want to play with how this looks like, we have a GunLab, similar to Tensor Playground, where you can actually play with it and see what's happening in the generator network and in the discriminator network. So play with it. You can, for every epoch, you can see what's going on, how the information flows, and so on. It gives you good insight in what's going on. So again, first I train the discriminator here. I will train it by improving the gradient such that it will be able, with the trained data, to distinguish between real and fake. And here I'm training the generator with in such a way that the output only generates real. So that's what I want to do. So this should be improved in order to get more real pictures, right? So that's what I'm doing over here. So after this one has been trained, you have a generator trained that will actually can generate pictures that look like other input pictures. So it will generate it. It can generate new pictures. Okay? So what can we do with this? Well, for example, create these enemy characters, new ones, quite easily. You put in some of examples and it will generate similar examples. Transform pictures like image and also image domain translation, the one that I showed you. This is an interesting one. Actually, it's a combination of a autoencoder with a generative adversarial network, and here you can see that I'm trying to influence and also train on, let's say, characteristics from these pictures. For example, this is a female, has black hair, and if we change the vector, we can output. Cool. We can say, okay, this is my original, and now I want to have the same person, but then with the glasses, for example. And then it will be able to output the similar picture, but then with glasses in a realistic way. I could use it to deblur images. If I do this deblurring, I can make it like this. I can generate video. I can generate music and so on. Could use it to generate, these are all non-existing cars. Could generate new cars. Right? So this looks like a BMW that has a different, yeah. It's quite funny to see this one. So as you can see here, it can be used also in the design process. And a variant is then StyleGAN, which looks like the one that maybe I can show it over here. Let me see. There's a website called This Person Doesn't Exist. And it's generating fake images of faces of people. So this is non-existing, and I can refresh it, and then it will generate a new face of a person that is not existing, non-existing person. So what we're going to see is a lot of stock video and photo material and all non-existing people, because then you don't have to pay any portrait rights anymore. Right?
Yeah.
So that's how it works.
So next step is movies.
Sometimes you can see it in the ears. It's getting better. Then in its face. Let me see.
You could
Our
replace
hands.
actors also, right?
Yes, you can.
It's cheap.
Yeah. Well, pretty good, right?
Yeah.
That's all what you can do with these type of GANs.
So
Okay.
make it good.
This is a variant called the StyleGAN. It's developed by NVIDIA. They make graphical processing unit or game cards and so on, processors. And StyleGAN 3 will allow you to generate these type of faces. Okay? Good. All right. Well, if you want to experiment with it, this is the way that you build a generative variance or a general adversarial network in TensorFlow. Here you have your generator with a number of layers, as you can see. I have a discriminator here. I'm using a specific type of activation function. It's called scaled exponential. Obviously, these are all things that people try to experiment with to see, okay, what works best, right? So they invented a new type of activation function specifically here. And here I'm defining my generic adversarial network. And if I want to run it, then you can see for the batch, I'm first training a discriminator and then I'm training the generator, okay? I'm not going to go into detail here in the code. You can, if you want to run it, try it for yourself, put in some image and see what it does, okay? The example that I have is creating new images that look like the fashion MNIST. There's also this famous database with clothing, I think in 10 different categories. And here you can see what it will generate. Not so good yet, but it's getting better and better. You can run it here in this code.
Even the first epoch was not so bad.
Not so bad.
No.
No.
It's the first.
The first training round. Yeah, it's pretty good. But still not really that
Yeah.
good. So again, new developments are continuing all of the time. And again, guns are nice, but they have some drawbacks. It's difficult to train, take a long time. So people invented something new. This is quite recent. We call it Stable Diffusion. You can already use it in your own PC. I have an example where you can, maybe we can try to run it over here. Let's see what happens. So what can it do? With Stable Diffusion, you can generate pictures, text to image, like these ones, or image to image. For example, you have this input image and you want to change it to, based on your text prompt, change it to other shoes in this case. or another environment or whatever. You want to change something in the picture, okay? That's what Stable Diffusion can do. Okay, again, what are the ingredients of the Stable Diffusion? Basically, it's autoencoder again. Here it's coming back again, because what we're trying to do is we try to learn a latent representation of this picture first, which is this one. So that's the first thing that we're going to do. Then I'm going through a process which is called diffusion. What is diffusion? Well, that's in timestamps adding random noise to the picture. So after timestamp T, I have a latent representation added with a lot of noise. You couldn't recognize anything again here. And the idea is that with a neural network, with diffusion, I'm going to denoise it again. But the denoising goes together with some conditioning, like I want to input some text that's being interpreted. For example, I want to generate Paris a Milky Way in this case. And I input it here also in the process to try to, change this latent representation to another latent representation and then decode it. So it's kind of a difficult process. If you want to dive into it, this is again how it looks. Encoding, diffusion, and if you zoom in these parts, these are convolutional networks again, denoising it with some input here, and going back to a latent representation, then decoding it to another picture.
But you also put a little bit text in, like a little
Yeah,
bit.
you
Is
can-
that a little bit similar like what you saw in the
Yeah.
previous one with the labels for black
Right.
woman and
That's a similar thing.
yeah,
But then not on the original picture or on this one,
yeah,
but on this one.
yeah,
Which is diffused
yeah.
latent representation.
Okay.
And it's something, that tried out, and this works quite well.
Okay.
So we will see probably a lot of these types of developments still. And this is the latest technique. I wanted to show you this to see, okay, how does this work? But I'm sure maybe in a year or 2 years' time there will be another technique, even a better one. But the ingredients are always the same. So the ingredients are autoencoding,
Yep.
like you can see over here, and the ingredients are trying to, change the latent representation in some way and train on it.
Yep.
In this case with noise, recognizing noise, and from a noise picture or present representation try to generate the picture again, which looks like, with some input, looks like other pictures. Quite complex, but this seems to work quite well.
Yeah, because why does it work like that? Because it is still an image that it tweaks on some knobs and then it inputs another version of something.
Yeah, it's basically a network that learns characteristics, and it will, and you can influence those characteristics by putting in text or other
The
images.
zebra did also, right?
Yeah,
Then it also recognized the zebra and then saw,
Yeah.
oh, this is for the skin color,
right.
and then tweaked the knob
Yeah,
and gave something else. It's
Yeah.
the same.
the same is happening here. Same process, same idea, but different, a little bit of a different technique.
Mm.
Here's a two-step process rather than a one-step,
Nice.
Because
basically.
with the zebra, you didn't restore it yourself, right?
Right. There's no, there's only tweaking, let's say, this part. It's basically this part trying to influence this one, generate, let's say, something looks liking, but then changing one part, one feature out of it into something new. In this case, you added, let's say, an extra diffusion process to it. Yeah. But again, with the, and this is all convolutional, right? Here we have a number of convolutional nets trying to learn from your input, because you have to decode or encode your input, your text that you want to have. And just
But you
set in-
convolute the latent image.
Yeah.
Cool.
Yeah. So you can run this stable diffusion technique on your PC. It's open source. You can download it. You have to have a GPU to have it to run quickly, or if you have a Mac M1 or M2, it can run natively as well. And runs also in Colab. So for you guys, I've included some code here that we can use to generate. Well, let's see, just for fun. how we can do that. So
But you have to train it with label data, right? Because you
it is already trained. So I
Yeah, yeah,
already
yeah.
have a trained network here.
Yeah, but it was trained with label data. Like here we see a house and water. And
Yeah, yeah, yeah. So I'm going to, I've included this on the canvas for you guys. As you can see, I'm running here GPU. So you have to select GPU to make it faster, right?
Question,
Yeah.
so this is a local run, or does it?
This is on the server. This is Colab, Google server. So now I'm running on the Google server.
On the Google server,
Right.
so that's quite a big installation.
Big installation with a lot of GPUs.
Okay.
Yeah, to get the speed. So we talked about Keras, which is the high level, language on top of TensorFlow. Keras also included, let's say, convolutional functions like the Keras CV. So I need to install that first.
Is that related to OpenCV or is it just?
No, it's not related to OpenCV. It's Keras Stable Diffusion implementation, basically.
And where does the CV stand? Oh, okay.
I think it stands for, let's say, picture recognition,
Yeah, okay.
picture
Yeah.
input.
Yeah.
Yeah.
Okay. Cool.
So I've installed it. I have to import it, which is called Keras CV, right?
Cool.
So I can speed up. I have a command here where I can speed up. I can set the floating operations for GPU and computing power separately, which I'm going to do. And this is the interesting part. I define the model here. Cool. Keras model, stable diffusion. So that's the latest one, right? I make it compile fast, and I want output images of 512 by 512 pixels. Okay. And let's see if I've set that right. I'm going to run it here. Okay.
We want to see you fast car.
Now something else. And it has to build it up, the model. It'll go pretty fast, but still we have to wait it. So here we are trying to build up the stable diffusion, which is then the autoencoder part and the diffusion part, which I showed you.
Is it then training or is it this picking,
No, this is-
downloading somewhere or
This is,
something?
this is building up the model, the trained model,
Okay, because
stable diffusion.
the,
trained
the, the
model.
whole training was already done.
Yeah,
Yeah.
yeah. Okay, good. Then, the most important part, I have to define what I want to have, what kind of... Now, I have some keywords here, but what do you want us guys see? What should we put in? What do we want what kind of picture do we want to generate? Anybody? Some ideas?
Heavenly.
Huh?
Heavenly.
Heavenly?
Heavenly. Like,
Heavenly?
Hemels.
Hemels.
Yeah, what? You have to be more specific.
To be more specific, I thought I'd give it like
For example, like an astronaut on a horse or something like that, or
Something engineering? Can we do something engineering?
dogs, people,
What's engineering?
some objects, some real
W
objects.
for the perfume.
Try to think of some, we want to see some objects in a funny way.
For the
Yeah, but it's
That's able to.
Mayday 40.
I can try. How do you write that?
Mayday 40, that's W40.
It's very
And
specific.
perfume.
Like this?
Yeah.
Yeah.
But I don't know
Maybe
if
not
it's-
fantasy art.
Okay.
Maybe.
Well, try it anyway. Try it anyway. Let's see. And then
En de Mayday 40 zelf parfum is natuurlijk niet handig.
Lady Phil, that's the
the
lock removal stuff, right? I don't know if it understands what it is, but it is
Shower gel if you want.
Yeah, shower gel.
shower gel, yeah. No idea what
Is it just input images?
Sorry?
Input images.
It already has been trained on images. So now it's taking, let's say, this data here, this to create the picture. I'm going to create three, by the way, three different. Okay. So let's see what it will do. It will take a minute or so because this is heavy stuff. Obviously, let's see. Article.
So download stuff.
Yeah, downloading data. Has to look for some data, and then I have defining a plot here.
Now it's okay. Oh, it's still okay.
Yeah,
Pretty quickly.
pretty
This
quickly.
is WD-40 and perfume.
And what is happening now in the because you also are training now. Or not,
Yeah, well,
This is epox or is it not epox?
no, it's not APOX. It's I think it's trying to decompress. How do you call it? Decode the pictures in steps. Yeah.
Okay. Yeah.
So that takes time. The decoding, obviously.
Yes.
But let's see.
Should there maybe be a comma between
Not
WD-40
really.
and perfume?
Not really.
Oh.
No.
And now we can. Yeah, in between.
Yeah.
Yeah. Oh.
Right side. Okay.
En nog geen, ja, ik heb wel gegeven. Ik heb nog geen medewerkers. Nee, alleen die parfumfles.
Perfumes here.
Yeah, but it's not there's no W4, not yellow and blue.
No.
No. Okay.
Too much fantasy.
Too much fantasy. Anyway, try it for yourself. I mean, what you need to do, run it in Colab, and then
Pretty cool.
here you have. I have here a cute magical flying dog, for example. If you do that, you get something like this,
Oh well.
right? So that's an example. Okay, so that's the latest actually in generative NL. We know about GPT-4, obviously. That's another. Actually, GPT-4 is using Stable Diffusion for generating the pictures, and GPT-4, as you know, is the successor of GPT-3, which is from OpenAI, and it's predicting words basically. And now in GPT-4 it can also predict and produce pictures, trained on large amounts of data. It's also encoder-decoder based, so auto-encoder type of networks, and it works in a conversational way. It's started in 2018. Here you can see how recent, how quickly things go. But this is only 5 years ago that they started with the first model. And now 5 years later, it's a pretty strong trained model. Okay. So yeah, why should someone learn about data science? You can ask that question, obviously. Well, it's becoming increasingly important. The fields of today's data-driven world. And it allows people to extract insights and make informed decisions from large and complex data sets. Right?
You do wrote this.
No,
Pre-trained.
it's pre-trade.
It's also
Okay.
trained by data scientists.
And it can also program. It can also program. Could you do
Yeah, they used it a lot, I think, with engineering fundamentals.
could you make a Python loop?
Yeah, who used it for EF?
Yeah,
So
yeah.
a lot of people used it.
Here is well, a simple one, a simple Python loop is outputting this. But, so you can use it for programming as well. How does it work? Just to finish off. In fact, there's a lot of human training has been going on in GPT, because the first step was that they hired 40 people that actually helped to train the output of a network to see. We have this question and we have this answer. So question and answers were, let's say, generated by real people.
Oh yeah.
Yeah. And we had about, I think, 30,000 input-output samples. That's how it started. So done by real people. And then, if you have your input and output, as you know, you could train a neural network to generate it from the data. Okay? Second step was to use this model and to generate, let's say, alternative answers on these questions here, and then give them values. So things like, okay, if you have 4 different answers, then you might want to know, okay, which one is better than the other. So you have k above 2 possibilities, like here in 4, you have 6 possibilities, and say, okay, A is better than B, A is better than C, A is better than D, etc., etc. Right? So you then have a trained model that can generate multiple outputs, and then the last step we use. So it's a lot of humans involved here in this step as well. The last one is to use reinforcement learning, as it's called, because now we have trained a model with alternative answers which have different values. So you could train a network to generate these values and to make it better to generate the best answer.
Wow.
Really. Right?
So you really train the network to see how much you should punish the other network.
Yeah.
Wow.
Yeah. And I think reinforcement maybe next week a little bit about it, I don't know. But
Yeah.
we'll see. But then again, you're training your network to produce the best answer because you're training on let's say your input was this over here. So, okay. All these developments, we've seen a lot of different models now coming up, like text to image, Midjourney is a famous one. They're all working with stable diffusion, so that's the latest picture generating technology. You see text to music, text to speech, text to video, this is the latest one. There's a 1 week old, generation 2, and also the big tech companies, they're working on this. The interesting thing is that GitHub and also Microsoft, they include what they call Copilot inside of their environments. So Microsoft will use it. You will see it in the Office products like Excel and PowerPoint pretty soon, where it will help you to generate content for your slides and your Excel spreadsheets, and also in Teams. And in GitHub, you know, where you can share your code and so on, work on your code, different versions. It will help you program. So that's the programming part. We call it Copilot. Okay. And this is the latest. This is the latest Midjourney version, based on stable diffusion, and generated video with Runway ML. And this is the so-called aging effect. So we have a picture here, and if we start moving this picture, make a V out of it, I'm generating a video where you can see how aging will evolve. Right? So, this is it. Okay, so far about the neural network part. Any questions about this part? I'm not expecting you to do anything in your, or we are not expecting you to do anything in your report concerning these type of neural networks. They are pretty complex. If you want to, you can. The CNN might be something maybe to try out. We have some groups that we're working with the CNN. So anyway, use a simple neural network that can help. So you need to do that. That's for sure. Maybe you could use CNNs, and maybe you could use, like, if you have time series data. I don't think anybody has. Well, maybe the football, the Golden Ball might be some time-related series, right? Can you predict, let's say, the next position on the list of, you know, where it will end on the Golden Ball competition? And yeah, for Thursday, again, look into if you can use these neural networks. Anyway, use NLP, the basic one. And again, we have a guest lecture of Volker Will trying to explain about how they use machine learning, pattern recognition, and so on in their daily job. Okay? Okay. Well.